Something that we see every day. A view with superimposed images, from different scenes. The reflection of one scene from a window, a glass pane, is superimposed with the direct view through the glass. Little attention is paid to such a thing. Except, when it is entertaining. More than a century-old optical illusion by John Henry Pepper, the superposition of a reflection and a scene, is still alive and well in the world of entertainment. This part of Chapter 4 is a reflection on the reflectivity of dielectric media. From previous presentation, it appears that the formulations of reflection of the two main polarizations, transverse electric and transverse magnetic, are quite symmetric. However, that is not the case in real life. The reason is that most dielectric media, such as water, liquid, glasses, polymers and many other optical materials, have different dielectric constant epsilon, which make them optically distinctive. Yet, virtually all have the same magnetic permeability μ, which is 1. As a result, TE and TM reflection and transmission have different properties, with important implications on applications. Here, TE and TM reflection difference can be seen with the green rectangle spanned between the reflected E and H field. The area of the rectangle, which is proportional to the E cross H magnitude, is proportional to the reflection wave intensity. At 0-degree incidence, there is no difference between TE and TM. At larger incident angle, it is evident that the TE reflection intensity increases monotonically, while TM reflection decreases, vanishes, before increasing again. The two polarizations can be compared by looking at their reflection coefficients. However, it would be a case of apple versus orange. The reason is indicated in the subscripts of the coefficients. For TE, it is the coefficient of the electric field, while for TM is it the coefficient for the magnetic field. To compare properly, it should be either electric versus electric, or magnetic versus magnetic. At 0 incident angle, TE and TM are degenerate, and indistinguishable. In fact, a 90-degree rotation would make them the same. If the two polarization reflections are to be compared, they should be identical. Yet, the TM reflectivity of the H field is not equal to that of the E field. As the incident angle deviates from 0, the symmetry is broken and TE and TM are different. The reflection E field of the TM case is projected on the interface, which is represented by the small green vector. This E field component is adiabatically related to the reflection E field of the TE case. They become identical at 0 incident angle. Hence, the appropriate comparison for TE and TM reflections should be based on the reflection coefficients of these two E fields. The comparison is now appropriate. Both reflections start out being equal in both phase and magnitude, as it should be, at 0 incident angle. As shown, the E field reflection coefficient for TM case is simply the negative, or 180 degree off the phase of the H field. It can also be verified by taking the limit of these expressions, as the incident angle theta is approaching to 0. The difference between TE and TM reflection is evidenced with a side-by-side comparison. At an incident angle known as Brewster's angle, the TM reflection vanishes. As it will be shown later, the reflection goes through a sign change, that is, a 180-degree phase shift, from negative, out of phase with the incident field for angles less than Brewster's, to positive, having the same phase as the incident field for angles larger than Brewster's. The TE reflection, on the other hand, only monotonically increases versus angle. A pair of polarized sunglasses can reveal the TE-TM difference in common daily surroundings. From the very beginning, polarized filters were already found indispensable in artistic photography. Polarized sunglasses are not just for improved vision but can help safety in driving by reducing sun glares in reflections from car glasses. All these effects more or less are consequences of the TE and TM reflectivity difference. It appears in a few previous pictures that polarized image differences are not only in reflection or scattering from a surface but also from the sky. In the previous chapter, Rayleigh's scattering was discussed to explain the blue color of the sky. The same theory can explain the polarization of skylight and associated effects on outdoor scenery in natural lights. Interestingly, there is a fundamental connection between these phenomena, that is, the polarization of dipole scattering and the reflectivity TE-TM difference, that will be discussed later. In a previous chapter homework, an assignment was to take pictures with a linear polarizer looking at the sky in a direction perpendicular to the sun rays. Unlike those pictures taken with and without a polarizer, the assignment specifically aims for the Stokes degree of linear polarization coefficient, in which the polarizer direction is specific, that is horizontal versus vertical polarization, such that the image field of view includes the direction looking into the quote-unquote donut hole of the dipole radiation angular distribution. Typical results are as shown here. When the atmosphere is clearest, the portion of the sky that is in the direction looking into the dipole donut hole, taken with vertical polarizer becomes darker, which is consistent with the expected vanishing of the radiation intensity from the donut hole. Separated into its red, green, blue components, the images show clear evidence of light polarization versus elevation view of the sky. For parallel polarization, the sky light intensity is nearly constant with respect to elevation, while the vertical polarization light shows a decrease versus elevation as expected. It is the direction looking into the quote-unquote dipole donut hole. This can be shown more formally as the Stokes degree of linear polarization. The three linear polarization images can be combined with false color coding. The clouds become darkest as expected, because random scatterings by water vapor in the cloud cause depolarization. As a side note, the bright edges of the cloud are just artifact, because the two images were taken with several seconds apart and that was sufficient for the cloud to move and change shape. This homework is simple but useful to illustrate several concepts in Chapter 3. The chart of TE and TM reflection coefficients shows that the E-field reflectivity starts out at negative, that is 180-degree phase for N2 greater than N1. As the incident angle increases, the TM E-field reflectivity shifts toward the positive, and hence, it must cross a point where it vanishes, which is the Brewster's angle. On the right, the chart of reflectance power, as being squared, shows the large TE and TM disparity is just not near the Brewster angle, but over a wide range of angle. This is a reason why, in spite of the fact that common light sources are unpolarized, there are a lot of linearly polarized lights after reflections from smooth objects in the surrounding. One very popular application of Brewster's angle effect was in the early days of lasers. To reduce the cavity loss as well as to avoid polarization mode competition, the laser tube or medium has its facets set, or cut at the Brewster's angle as illustrated. Even with the advances of anti-reflection coatings, non-semiconductor solid-state optical amplifiers are still often used with a Brewster's orientation relative to the beam. The pictures show the optical amplifier slabs at the Lawrence Livermore National Ignition Facility being tilted at the Brewster angle. The larger the difference between the two medium refractive indices is, the higher is the reflectivity. These plots show the reflectivity as a function of the transmission medium refractive index, given the incident medium refractive index being 1. There are many applications that are sensitive to even small reflectance, especially in lasers or optical amplifiers, which is why there is anti-reflection coating technology that can reduce the reflectance to 10⁻⁻⁴ or 5. Even for prescription eyeglasses, it is generally found that users prefer to have anti-reflection for optical polymers with refractive indices between 1.5 and 1.67, for which the different reflectances may appear numerically insignificant. The reason is that the human eye is sensitive to low light level, that even a reflectance difference of 1% can matter to the comfort of the vision. One noteworthy aspect about the vanishing TM reflectance at the Brewster's angle is the geometry of the reflection and transmission k-vectors, as shown in the graphics. The Brewster's angle changes as a function of the transmission medium refractive index, but the two k-vectors are always perpendicular. This can be seen with a little algebra. These steps lead to the result that when two k-vectors are perpendicular, or when the sum of incident and transmitted angles is pi/2, the TM reflection vanishes. However, it is worthwhile to think in a more physically intuitive way, as we will see next. Consider a wave transmitting into the second medium. Imagine the microscopic physical process. Zoom in on the atomic or molecular scale. There are many atomic or molecular dipoles oscillating. Their dipole field together with the E field, give the displacement field. The reflection wave is the coherent re-radiation of the surface dipoles of the medium. For this TM case, the dipole polarization is in the plane of the incident, and hence, at a certain angle, can be parallel with the k-vector of the reflection wave. Then, the E field of the reflection wave that looks into the dipole donut hole should vanish. This is a physical explanation for the Brewster's angle vanishing reflection. From this perspective, the orthogonality of the two k-vectors, reflection and transmission, for vanishing TM reflection is not a mathematical coincidence or curiosity, but a manifestation of two simultaneous electromagnetic behaviors, the EK orthogonality of the transmission wave, and the vanishing of dipole radiation at polar angle of the medium surface atomic or molecular dipoles. In comparison, TE and TM reflection difference is thus based on a fundamental difference in the geometry of the E field and the induced atomic or molecular dipoles for the two polarizations. To summarize, reflection is an important effect in structures made of materials with different dielectric constants. In general, the higher the difference between the indices of refraction, the larger is the reflection. Furthermore, one of the most important properties is the large difference between the two polarizations, transverse electric and transverse magnetic. For the latter, the reflection can vanish entirely at an angle known as Brewster's angle. Lastly, it is worthwhile to note that the physics of the blue sky and its polarization contrast as studied in Chapter 3, and the TE-TM dielectric reflection difference discussed here, are not as disconnected as they seem.